Conservation of energy is a straightforward six-step process. The main idea is that the total energy of the system remains the same. So let's track the total energy of the system. First, you have to find the total energy in the system. Check in with the problem before anything interesting happens. Is there room to fall? Is something stretched? If either of these is true, record how much potential energy you have. Is anything moving already at the start of the problem? If so, record how much kinetic energy you have. Add up your total mechanical energy in the system and find the total energy. Now, if conservation holds, and it does, the total energy in the system should remain constant. After something interesting has happened, fallen, bounced, launched, gazorched across the room, the total energy of the system should still be the same. Take your total energy and copy it, character for character, number for number, into the column afterward. After something interesting has happened, check in again. Your total kinetic and potential energy, plus whatever internal energy you have because friction did work, will still equal that same amount. That way, we're not just doing conservation of mechanical energy, we've accounted for everything. Check in after the interesting event has happened. Is there room to fall? Is anything still stretched? Is it moving? Did friction do any work over the course of the problem? If so, how much work did friction do? Because that's how much internal energy you have. At this point, you should have enough information to solve for anything interesting you should be looking for, including a location, a velocity, or anything else. Here's our first example, the archer. 3-year-old Shivani Chekruni, the 388-point-winning Indian archery champion who's just earned herself a place in India's equivalent of the Guinness Book of World Records. So, Shivani draws back her bow, a stretch distance of A. The bow has a spring constant of K, and she lets fly the arrow. The arrow flies very, very, very fast with minimal drift to hit square in the middle of the bullseye. How can we control for how fast the arrow flies? How fast does it fly? Set up your work in 2 columns. First, analyze what's going on before Shivani shoots her arrow. Check in with potential energy, kinetic energy, and find the total. Pause the video now, show your work. When you're done and ready to check in, press play. In your 2-column setup, in your system, you should have potential energy. Absolutely, spring potential energy, 1/2 Ka squared with a stretch distance of A instead of the letter X. Kinetic energy, no, because before she fires the arrow, it's not actually moving. Grand energy total, 1/2 Ka squared. Now analyze what happens after she shoots the arrow. Your first step, do not scream, do not panic, do not even think at all, is to recopy that first line, 1/2 Ka squared, brain go off, fingers go on. Now that it's copied, that's how much energy you have to spend. You have exactly 1/2 Ka squared. So you take it from here. Do your after column. Analyze, is there potential energy? Is there kinetic energy? If so, how much? Solve for V, the velocity of the arrow. See if you can do the whole column yourself to solve for V. If you get stuck, continue with this video. Otherwise, press pause now and see how far you can get. As we said, the total energy is 1/2 Ka squared. There is no spring potential energy after she's let fly the arrow because the bow is no longer stretched. How much of the energy is kinetic energy? Well, assuming that there's no air friction on the arrow, we've got no internal energy, no potential energy. That means that all that 1/2 Ka squared goes into kinetic energy. We've got 3 kinds of energy, 2 of them don't exist. All 1/2 Ka squared of energy, the whole total, 100% of it, should go to kinetic energy. Now we know the formula for kinetic energy is 1/2 mv squared. If you got stuck up to here, pause now and work out the rest of the algebra yourself. If you've done something sensible, like canceling out these 1/2s and dividing by m, you should get a nice little square root for your velocity. Notice I started off with a proper high school haze. I did not give you any numbers. It's actually most efficient to do these conservation of energy problems in letters, even if you don't have numbers. I'll show you why. Terry Pratchett is a British fantasy, satire, and comedy writer who lampoons the real world with a little touch of magic and a big touch of nuclear physics. In his Witches series, the three witches of the classic fable get a new twist, including our central one, Granny Weatherwax, the oldest and grumpiest of the three, whose rickety old broom needs to be run around the garden in order for it to properly start up. In fact, it won't fly until it gets to a fixed speed, which makes it terrifically inconvenient for long journeys and emergencies where she has to save the world. In the novel Witches Abroad, during her climactic confrontation with the evil fairy godmother, who is heteronormative and fantasy normative in the extreme and wants to control everybody's life, after all, why be happy when you could be normal? Granny Weatherwax gets pushed off one of the pointy blue castle towers to her doom. Of course, she had her old broomstick in her hand, but I assure you, no time to run around and start it up. So, if that broomstick needs to be going 8 meters per second already in order to fly, and she gets pushed off a tower 12 meters high, should we be bemoaning her death and planning her funeral like all the other ugly, grumpy, but fundamentally good witches in the book? Set up the problem before and after. Granny starts at the top of a tower 12 meters high and is pushed off. That means she starts from rest and falls. Pause the video, see if you can set up both columns. We are trying to figure out whether her broom is going to lift off. Confused? What are we solving for? There are two ways to do this. Either you can solve for her velocity when she's at the bottom of the tower, or you can solve for a height. Still confused? Well, tell you what, if she's going more than 8 meters per second by the time she hits the ground, her broom will have taken off already. If she's not, splat, we will need a new main character. Alternatively, we can ask the question, when is her broom going to go 8 meters per second? She's falling from a tower 12 meters high. If she needs 24 meters to get up to speed, then that's going to be bad news for the rest of the series. If she needs less than 12 meters, she should be good to go. Pick which variable you're going to solve for and take it away. Everybody's before columns should look identical. Specifically, potential energy. Yes, there is most certainly potential energy. There's quite a lot of room to fall at the top of that tower. Kinetic energy. Well, not so much. She's starting from rest. Anything else? No, she hasn't loaded herself into a giant slingshot. Total energy, mgh. Brain goes off, hand goes on. First thing you do is you recopy that to the other column, mgh. Now it's a question of what you're solving for. I solved for height. Afterwards, you most certainly do have potential energy. You have fallen only part of the way. In that case, it's not true that all of your total energy goes to kinetic energy. You need to save some for potential and some for kinetic. Assuming that Granny is not wearing a giant parachute, which frankly would have solved the problem to begin with, we're going to assume friction does not do a whole lot of work. There's no air drag. And so, our total minus our potential gives us our kinetic. We had mg, our original height, to start with. We still have some mgh left, but all the rest can go to kinetic energy, 1/2 mv squared. There, that's not so bad. Multiply both sides by 2. Cross out those n's. 1, 2, 3. Check. Is there an m in every term? Why, yes, there is. They can cancel out. That's why I really recommend going with these letters. If you started with the 12 meters and the 8 meters per second, you're going to be at the stage pretty soon when you discover that Granny Weatherwax, inconvenient main character that she was, neglected to weigh in at the beginning of the novel. We have no idea how many kilos she is. Good news? Doesn't matter. Mass cancels out. You have a nice little solution for v squared, and having solved either for velocity or for height, you'll find that at a height of only 8.7 meters, that's 3.3 meters of falling, that's barely a few stories, her broom will kick in and she will be perfectly fine. See you in class.